Okay, so hi everyone. My name is Doreva Friamar. I am an MS graduate, and today I'm going to present to you our work of neural congealing. Was a work in collaboration with Michal Geyer, Yoni Kasten, and Tali Dekel, and we also presented it in the last CVPR. So in this work, we address the task of joint visual alignment. What do we mean by that? Given a set of images that are semantically related, our goal is to detect and align the most common content across the set, which, as we can see in this case, is the butterfly. Meaning we want to jointly align the images such that we learn dense mappings for each image, such that after transforming the images, each semantic part will be warped to the same location. So all the left wings are mapped to the same area together with the bodies, etc. And this results in dense correspondences between the images. Now, a nice visualization that we can do is to look at the average image before and after the alignment, where we can see that after the alignment, the common content is clearly visible. Now, a cool application for this is that together with the learned mappings, we can use this image as a template for editing. And we can do that by applying some edit on this average image just once, and then automatically propagate this edit to the rest of the images. And we'll see a few more editing examples later on. So the general task of joint alignment of images is not new and actually dates back to the early 2000s to the seminal work of Gunjiling by Miller et al., where they showed that images of a dataset can be jointly aligned by learning a per-image affine transformation in an unsupervised manner. However, this worked on datasets with limited appearance in variation like binary digit datasets. So a more modern approach was introduced by Gunjiling that proposed a GAN-supervised method for densely aligning an entire domain, for example, cats. Now, instead of learning a per-image transformation, they used a spatial transformer network, STN for short, that given an image, it predicts a 2D sampling grid with which they can backward warp the image. And notice that these transformations are more complex than just affine transformations. So in order to train the STN, they used a pre-trained style GAN to generate images, as well as use its style pose disentanglement for training supervision. So they got really impressive results at inference on complex data. However, they do hold a few downsides. So first of all, they require style GAN that is pre-trained on the images which we want to align. And after that, they need to have additional extensive training for learning their mappings and their common mode. Also, they are restricted to the final mode that was learned across a whole domain. So for example, with what we see here, if we were to have a set of cats that contain both their heads and their bodies, this case would give us still only the alignment on the upper part of the cats only. So what we see here, on the other hand, we propose a test time optimization framework, which works on small in the wild image sets. And by that, we mean as small as 5 images, and without the need of any additional training data. And our framework is trained end-to-end in a self-supervised manner. And since we train only on the given image set which we want to align, we converge to the common mode of that specific set. So now the big question is, if our only input to our framework is the given image sets, where would we get the proper supervision for the visual alignment? So we take inspiration from the tremendous progress in representation learning and leverage a pre-trained DINO-ViT, a vision transformer model that was trained in a self-supervised manner. And more specifically, a recent work by Amir et al. Showed a thorough analysis on these internal features. And we can see here a PCA visualization for the keys of the attention layer of the trained model, specifically of the last layer. And we can see that we can obtain semantic representations with very high granularity. And apart from that, they also showed that this encoded representation is shared across different yet semantically related object classes, like we see here in the animals that all share the same semantic parts like ears, eyes, etc. And so we want to leverage the power of these DINO-ViT features for dense correspondences and to use it as our guiding signal for our task. So just to understand the high-level approach of our method, given a set of images, we aim to learn a joint 2D atlas that represents the most common semantic content in the given set, which is to say, the common mode of the DINO-ViT features across the images, which, like we mentioned before, we refer here specifically for the keys that have embedding dimension of size t. So in addition to that, we also learn a mapping network such that each semantic part of the object across the set is warped to the same location in the learned atlas. And also note that the learned mapping is from a point of the atlas to a point in the image, and that way we can backward warp the images into the joint space. So the main idea here is that our method learns to jointly align the images in the DINO-ViT feature space. And we learned both the mappings and the joint atlas simultaneously. And just to note that in practice, we use a spatial transformer network in order to learn the transformations, like in Gunjiling. So in more detail, given the set of images, we use a pre-trained and fixed DINO-ViT model to extract the image's keys from the deepest layer. The mapping network predicts dense mappings for each image, which are used to transform the DINO keys to the joint space, where, like we said, we have the learned atlas keys. So then we apply the keys loss to match between the transformed keys and the atlas keys. Now, since we're dealing with images that are in the wild, we don't only have to solve the alignment problem, but we also need to detect what is the most common content, while also ignoring the cluttered background of the scene, including any unrelated objects, for example, the laptop that we have over here, or the bunch of coffee beans in the background over here. So for that, we also define a saliency value at each atlas pixel, which holds a value between 0 and 1. And for optimizing the atlas saliency, we extract initial saliency masks for the images. And these masks are estimated from DINO-ViT features in a pre-processing step using the proposed method by Amir et al. And they give us sort of an initial guess and guidance as to where the most common areas are. So similarly to the keys, we warp them to the joint space and apply a loss to match between the atlas saliency and each one of the image saliencies. And we'll see the formulation in a bit. So just to get the feeling of what it looks like during training, so we can see here how we learned both the transformations and the joint atlas at the same time in order to get the final dense correspondences. So our final objective function consists of 4 different terms, where in addition to the keys and saliency loss that we just mentioned, we also apply regularization terms both for the mapping and for the atlas representation. And we're also going to follow this small example just to see the effect of each loss term. So we see at the top row part of the original image set together with the final aligned images at the bottom row. So our driving loss is the keys loss, where we want to match the learned atlas to each one of the transformed image keys. And it is a combination of MSE loss and cosine distance. But an important thing to note is that we also mask this loss using the atlas saliency. And that is for aligning only the common parts because we don't want the keys in the background to interfere with the convergence. So what happens if we don't use this loss? As we may expect, the alignment has no semantic meaning and just mainly follows the initial saliency masks, which in this case are pretty accurate, and we just don't get any meaningful alignment. Next, like we said, we wish to match the atlas saliency to each one of the transformed image saliencies. And you can think of it sort of as a saliency voting loss, because each image just votes which pixel in the atlas should be salient and which should not. Now, since the image saliencies are often very rough and contain clutter or irrelevant salient objects of the scene, we use a robust loss, more specifically a Huber loss with delta of 0.7. And just as a reminder, within the regions of this parameter of delta minus delta delta, it acts like an L2 loss, and outside those regions, like an L1 loss, which is more robust to outliers. So this allows us to get less punished for the noisy areas, which we don't want to include. For example, the noise that we see here on the right. And here we actually ablated what would happen if we weren't to use the saliency masks at all, since we don't have a saliency loss and no supervision for the atlas saliency. And we can see that the model really struggles to converge with all the relevant noise that it has in the background. Next, we have the regularization on the mapping network. So let's just first see what it consists of. So like we said before, it's a network that gets an image and outputs a sampling grid with which we can backward work the image. And the network actually consists of two different networks. The first one is responsible of predicting the parameters of a similarity transformation, rotation, scale, and translation in 2D. And the second predicts a dense 2D flow grid, which is a grid of 2D displacements. And the outputs of these networks are then composited together to obtain the final grid. And so we regularize both networks in order to make sure not to converge to a single point, and that the shared representation will be as undistorted as possible, meaning we want the similarity transformation to do most of the work, but still allow some distortions for aligning objects with different proportions of semantic parts. And we can see that if we weren't to regularize the mapping network, we actually provide too much freedom to the unconstrained part of the mapping, and it just spreads in total chaos. And finally, we also regularize the joint atlas. So we apply sparsity constraints, meaning we want the atlas to be as sparse as possible. And this is important for cases where many of the initial saliency masks contain a lot of noise or irrelevant salient objects. And in addition, since the position of the shared content in the atlas is arbitrary, we also apply a center loss, which is computed by a weighted average of the atlas coordinates using the atlas saliency. And so we just define the center of the atlas to be the origin. And we can see in this example that we get that without this loss, we indeed get the object is not centered and even drifts outside the atlas boundaries. So now let's see some results. We are going to see the given input sets together with the initial saliency masks extracted in pre-processing, and the final result of the aligned images. We can further visualize the average image like we saw before in the joint space by simply averaging out the images, the aligned images, and also a PCA visualization of the atlas keys. And this actually emphasizes the different semantic parts of the common object, and finally also the atlas saliency. And notice the set contains large variations in appearance, structure, and pose of the common object, as well as background clutter or other distracting objects that are also present in the initial masks, as you can see in this row. Also, even in cases where over here that it contains the entire Lego man. And still our method was able to detect the most common content and align them well. And our framework also supports horizontal flips. You can see that in some of the images, the handle is on the right in the mug. In other cases, it's on the left. And so our method is able to detect the best orientation and transformations for obtaining dense alignment. And since we said we allow minor distortions, we can also handle objects that have different shapes and proportions between semantic parts, like, for example, over here where it's stretched the neck, or here just squished it, and this in order to really match all the semantic parts between the images. And our method also works on sets containing images across different domains, such as we have here a painting of an owl, a statue, crochet doll, or just a real owl. Here we can also see an owl made of coffee beans. And since they all share similar representations in the DINO-ViT space, this allows our framework to align them well, also in cases of sleight of plane rotations. And here we can see an example of a set of images across different classes, and which all share, again, a similar representation in this space. And another example over here across different domains, also with very large differences in scale, or as we said before, different proportions, for example, the distance between the ears of the cats. So now let's see a few applications that we can derive once we have the learned mappings and the joint atlas for a specific given image set. So like we saw in the beginning, we can apply an edit on all the images in the set in a very simple way. We can simply average the transformed images as we see here and use it as a template for editing. And then we can use the learned mappings and automatically propagate the edits to the original images. And this is straightforward since we know that each point in the atlas, we know where it is mapped to in each one of the images. And just notice that the edits are mapped correctly to the same semantic regions in all images. And we can also extend it to work on videos. But just to note that since videos have a lot of abundant data, meaning each frame is pretty similar to the one before and after it, we actually don't have to train on all video frames. We can instead train a model only on a subset of representative frames, and then at inference, we pass all frames and apply the edits as before. And another application we can obtain during inference is semantic point correspondences. So this means that given a point in image A, we wish to find its corresponding point in image B. And the way we can do that is that by mapping the coordinate from image A to the joint atlas space, and this is done using the mapping of image A, and then back to image B using the mapping of image B. And with that, we can also numerically evaluate our method. So we do that by measuring PCK transfer on a couple of datasets, one of which is the cub dataset. And we can also see here a numerical as well as visual comparison to Gunjiling, where we have part of the given image sets together with Gunjiling's and our results. And we can actually see here an example of extreme changes in orientation of the common object across the set, a bird with its wings widely spread, another with the wings closed. And we see that both Gunjiling and our method struggle to align, but Gunjiling sort of fills the missing parts of their template, whereas our method manages to align the heads of the birds, since it really works according to the common semantics across the set. And here we show another comparison using a set of images across different domains. And we can see that Gunjiling struggles to generalize to such domains, while our method successfully aligns sets such as this one. So regarding the limitations of our method, since we align the images in the DINO-ViT feature space, we rely on these features to capture the semantic association across the image set. So if it does not happen, our method won't work well. Also, we saw the cases of extreme topological changes in the common object across the set, which our method mostly struggles due to rigidity constraints. And we also noticed that in sets containing symmetric objects with large rotation differences, the relative position between parts may affect the convergence and may lead to partial alignment, like we see here, where it matched the left eye of this cat to the right eye of the rest of them together with the nose. So this happens with symmetric objects. And just to mention that in general, our framework is not designed to align images depicting more than one instance of the shared mode. In such cases, like here, our method may arbitrarily align just one of the objects, or in other cases may fail to converge, like here that it just squished them together, which also affected badly the overall convergence for this set. Thank you so much for your attention. You're welcome to visit our project page and to see more results and code. If you have any questions, feel free. Thank you.
So it does look like we do have a question in the Q&A from Shad, if you want to take a look at that.
Yeah, let's see. So it says, are the edits in real time? Could someone have a live video feed edited in real time? So no, it does not work in real time. We train on our specific video and then apply the edits at inference.
All right, final call if there are no questions or additional questions. I think that's it. Oh, yeah, we do have one more follow-up.
Oh, just a sec. Actually not sure that I understood the question. Okay, so the mapping, regarding the mapping network, so we said that it consists of both a similarity transformation and a non-rigid transformation, which is simply like in a flow grid where you have, for example, an optical flow in each location, how much you move this point in 2D. Other than that, it's just the main thing that how we write it in code. But if you're asking specifically in well, yeah, more than that, I guess that we can take it offline and I'll be happy to answer more than that. And do we have to think in 3D? No, so all the transformations are in 2D. I mean, we do manage to work with slight out-of-plane rotations, but not too much. I mean, it's just 2D transformations.